Bene, allora benvenuti a questa terza lezione su NetLogo. Ho ricevuto un suggerimento da parte di uno di voi per realizzare un modello che però mi sembra, alquanto complicato, di diciamo, delle specie di polimeri che aderiscono su un substrato di oro, ehm, diciamo molto interessanti, però mi sembra alquanto complicato. Allora volevo cominciare, diciamo chiaramente se ci sono suggerimenti anche diciamo immediati, si può fare alcune considerazioni, eh. Se no vi volevo far vedere, una diciamo possibile, diciamo modellino semplice, diciamo che riprende un modello che ho fatto tanti anni fa di, modellizzare una reazione di catalizzazione su un substrato. Allora link, teaching, complex word. Allora trovate il link e ehm, il link e le lezioni sempre su questo vi segnatevelo, è sempre lo stesso, cioè sia il link per registrarsi, sia, ehm, il coso, diciamo materiale e la registrazione delle lezioni. Allora quindi l'idea è la seguente: supponete che questa qui sia la superficie di una marmitta catalitica, ovvero una superficie su cui certe reazioni possono avvenire più facilmente. E, diciamo che ogni patch, supponiamo che, voglia avere differenti colori che rappresentano l'adesione di, che ne so, particolari molecole. Ehm, e l'idea, diciamo, quello che avevo fatto tanti anni fa, guardiamo se ritrovo anche questo qui, un articolo su transizioni di fase. Allora l'idea è la seguente, che, proprio come funzionano le marmitte catalitiche, si vuole favorire la combustione di monossido di carbonio, che potrebbe essere appunto prodotto da una combustione incompleta nella camera di combustione, facendola appunto reagire su una marmitta, tipicamente su una superficie di platino, se mi ricordo bene, non sono un chimico, con ossigeno. Il fatto è che mentre, C e O sono, molecole legate molto strettamente, quindi non si dissociano sulla superficie, quindi essenzialmente le possiamo considerare come se fossero una sola specie chimica. L'ossigeno invece viene praticamente adeso e quindi staccato i 2 atomi di ossigeno e poi possono, se sono adiacenti sulla superficie, una molecola di CO e un atomo di ossigeno possono reagire formando CO2 che si distacca lasciando 2 siti liberi. Quindi questa è un po' l'idea. La li Ovviamente si suppone che la reazione sia fortemente sbilanciata in maniera che non ci stiamo a preoccupare delle reazioni inverse, cioè non c'è possibilità che la CO2 si trasformi in CO e ossigeno, e quindi questo qui facilita un po' il conto. Ehm, Ci sono tutta una serie di considerazioni che ovviamente saltiamo. Veramente per fare il modello adeguato bisogna andare a considerare temperatura, energia. Noi chiaramente semplifichiamo un po' tutto, e il problema non è banale, soprattutto non è banale che cosa succede con la migrazione, cioè il fatto che sia il CO che l'ossigeno possono migrare sulla superficie. Questo perché se voi non mettete la migrazione, vi farò vedere che appunto il modello che faremo oggi, c'è una transizione di fase, ora qui non c'è poi riportata, ma insomma, essenzialmente la finestra in cui avviene la reazione è molto, molto piccola. Praticamente succede che, il modello dà o avvelenamento da CO, che vuol dire che tutta la superficie si ricopre di CO e l'ossigeno non riesce a attaccarsi e quindi, la reazione non va avanti, oppure avvelenamento da ossigeno e che è uguale, cioè la superficie si ricopre di ossigeno e non riesce a partire la reazione. In realtà credo che l'avvelenamento da ossigeno negli esperimenti non succeda, perché l'ossigeno può anche reagire con della CO direttamente gassosa e quindi non c'è. Però insomma, diciamo, per fare questo modello proviamo un po' a farlo così. Quindi l'idea è la seguente: noi abbiamo questo sistema, diciamo che nero vuol dire nero vuol dire mettiamo white. Okay, nero e qui mettiamo rosa, red. Okay, nero vuol dire che non c'è niente. Bianco vuol dire che c'è, mettiamo CO, e rosso o blu, che c'è ossigeno. E l'idea quindi è di avere degli slider che controllano le pressioni parziali, se volete la probabilità di adesione di CO e di O2. L'ossigeno può aderire solo se ci sono 2 siti vicini liberi, se no non ce la fa. E poi, un altro slide potrebbe essere che la probabilità di reazione tra quando sono vicini, chiaramente legata alla temperatura, se la marmita è troppo fredda non c'è questa reazione. Quindi cominciamo con un classico bottone setup, poi mettiamo un paio di slide che potrebbe essere, che ne so, la probabilità di adesione di CO, mettiamo da un punto 0,1 fino a un massimo di 1. Ora poi bisognerà discutere un momento su come interpretare queste probabilità. Poi possiamo mettere un'altra slider che è, questo non è un corso di modellizzazione di materiale, adesione di O2, mettiamo sempre tra 0,1 e 1. Un altro slide potrebbe essere la reazione CO2, CO, sempre con una certa probabilità. E poi qualche parte. E poi vabbè, mettiamo un classico bottone Go Forever, che dovrebbe far andare avanti la reazione. Allora, mettiamo il codice qui vicino. Allora, l'idea è di provare a modellizzare tutte queste reazioni come reazioni per una patch, no? Quindi diciamo patch is uno status, con l'idea che status uguale a 0 vuol dire empty, status uguale a 1 CO, mettiamo, e status uguale a 2, tutta questa roba ovviamente andrebbe messa nella info, anzi mettiamocelo, ora si mette anche nella info, status uguale a 2, O2, perché ci siamo, proviamo anche a utilizzare il tab info. Se uno clicca su help, su edit, diventa un linguaggio tipo wiki, dove questi qui sono intestazioni, e quindi this is a simple model of an irreversible catalytic reaction among CO and O2 molecules. How it works, okay, just for writing something. And so now if we click on edit, you see that in this way you can document the status of the code that you are writing. Okay, so and then we can have to set up clear all as usual. Ask patches. This is not really needed, but at ask patches set status equal 0. We can begin by having all patches empty, and I don't know, recolor. We can define a subroutine to change the color of patches that are updated, and reset ticks to start the clock, and so essentially this should also to recolor. This is a procedure for patches. So set pico. No, we can if else status equal 0, set picolor black. Then I can discuss this status equal 1, set picolor white, else set picolor red. Okay, let me discuss a bit how this recolor works. First of all, we can set status 0, not equal to 0. Check. Okay, so this is working. So how it works? If else, as you can imagine, is an if and an else, but in reality it can also take several conditions, like a switch in other languages. If you use it with more than just a default, a test and the default, you have to put a parenthesis around all of this. So normally you use it like if else x equal 3, I don't know, set or ask turtles to do something. Else ask patches to do something. So this is the default use of if else, and in this case you don't need the parentheses. But if you want to put more than one condition, then you have to put everything in parentheses. And now for formatting is better if you put the test on their own line so that it can be indented. So you can write if else equal x equal to 3, do something with turtles. X equal to 4, ask links or do. And finally, this is the default. This is the default. Do some other things. So in this case, if x equal to 3, do something. If x equal to 4, do another thing. And otherwise, if this is fulfilled, this one. But in this case, you have to put everything in parentheses. And if you write in this way, you have a kind of nice indentation, so that if you type tab, it is automatically reformatted in this way. This is one way of writing this. Actually, you could write also in another way. So let me comment this. You can also use, instead of if-else, the reporter version. So set pcolor if-else value. In this case, it is exactly the same, but it returns a value. So in this case, if-else value status equal 0, black, status equal 1, white. No, someone want to participate. Okay. And finally, the default is red. Okay. So this is the equivalent version, but instead of, say, using a procedure for different cases, you can return a value for different cases. So this should work exactly the same in this case. So it is up to you to choose which one is preferred. Okay, so up to now we have just reset everything, and now we have to write the real body, say, to go. And so we have to decide. Clearly, we can take one patch at random. So ask one of patches. So we take one patches at random, and according to its state, it can do several things. So you can if-else status equal 0. So here we can put all kind of reactions that can be done if its status is equal to 0. Other ways, status equal to 1. Other ways, this is the default, status equal to 2. So this is the default. Or if you want to be more clear, you can say, write here status equal to something, and then the default, which should never occur. Say something like user message, this should not happen. So if you just, in this way, I think it is more clear what to do instead of using the default just for doing things referred to a given status. This should be in a more readable way. Okay, so let's start with the simple cases. In case it is a CO, and if I have one O and more in the 4 neighbors, if any neighbors 4 with status equal to, or color equal red, as you want. So if you have at least one neighbors with the status equal to, with probability COO, if random float 1 less than COO, do the reaction. So you become status equal 0, you are free, recolor, and you ask one of neighbors with the status equal to no status equal, set status 0. I can never remember how to change the value of a variable. Okay, so this is a procedure. I don't think it is correct because it has the same probability of reaction regardless of how many neighbors have the status equal to 2. Actually, I think that in order to, I have to do some calculation, but I think that in order to be more accurate, you should compute the probability of assuming that this CO can react with any neighbors with the same probability in independent processes, then here the probability should be it should not happen if neither of neighbors can react, but let for the moment take this one. Okay, this is essentially the same for status equal to 2. So if any neighbors with status equal to 1 with the same probability, and you ask one of neighbors with the status equal to 1 to react. Otherwise, let's assume that we have status equal to 0. In this case, if it has at least another a neighbor with also which is also empty, it can occur that O2 the O2 molecule can attach to the surface. Otherwise, only a CO can be attached. So if else any neighbors for with status equal 0, so this is essentially, then we fill CO or O2 can attach, can absorb. Else only CO, so if random float 1 less than a CO, set status 1 recolor. Okay, so this is the simple part. Now we have to decide what to do if both CO and O2 can absorb, because we have two probabilities here that we have defined them as, say, from 0 to 1, 0 to 1, but clearly this is not really correct because essentially the sum of the two can be greater, so up to 1. I mean, these are essentially the probability that in a given patch hits either a molecule of O2, either a molecule of CO, or a molecule of air. So they are essentially proportional to the partial pressure of CO and O2. So this is not really correct. But assume that the sum of the two is less, okay, it can be. So if it is less than 1, the sum of the two, it means that we have a very small amount of things. If they are greater than 1, it means that they saturate the air. This is not really correct from the point of view of physics, but just to arrive to something. So if random float 1 less than ACO plus AO2, actually this is not really correct. So should be, say, 1 minus ACO times 1 minus AO2, which is also really probably not correct. So the idea is that the probability that nothing absorbs is the probability that nor CO nor O2 absorbs. So if they are independently relevant, this is the probability of not absorbing a CO, and this is the probability of not absorbing NO2. So this is the probability of not absorbing anything, and so 1 minus this is the probability of absorbing something. So if something absorbs, then if random float 1 less than the relative probability of one of them, say ACO divided by ACO plus AO2. So the logic is this one. This is the probability of not absorbing CO. This is the probability of not absorbing O2. This is probability of not absorbing anything, so this is the probability of absorbing something. If something absorbs, this is the relative probability of absorbing CO with respect to O2. And so set status 1 recolor. Otherwise, set status 2 recolor. But since O2 absorbs with on 2, I ask the other neighbors. So ask one of neighbors 4 with status equal 0 of set status 2 recolor. Oof. So I hope this is essentially finished. So let me check. I have to close this if else at the end here, I think. So here, check, recolor if this is only if else. Okay, so I hope that, so you see, this is not really trivial. Essentially, NetLogo is not a shortcut for doing modeling of any kind. It can be useful for, say, managing lists and agent set, but the computation is always the same. So let's see what happens. For instance, we can also make a button step that ask go, but just for one step. So you see that oxygen always absorbs in pairs, while CO absorbs singly. Then, okay, if we go, you see, in this case, it is all filled by O2. We can increase the partial pressure of CO to see what happens. You see that now the transient is longer, and probably at a certain point, okay, we have a transition to the poisoning of CO, and in the middle there are small windows in which we can have a coexistence of say of CO and O2. So, but okay, now another things that we can do. Okay, suppose this is the first version. We can save it. Say in the here my drive NetLogo 2000. No, this is not. I don't remember. Where I put probably in the attachment. Okay, it is in complex word, not in Unifi. This should be here. NetLogo 2025. Okay, so this is let's say catalyst 1. Okay, let me check if it appears in the folder. It should appear here among these. Okay, this is the file, so you can check it. And so improvement, a first improvement can be, okay, I would like to have, say, given a certain reaction probability, given a certain say partial pressure of O2, a complete scan of say what happens with ACO, and maybe have some plot. So suppose that I want to have a plot here. This is the coverage of the surface, and so I have one pen which plot count say patches with status equal 1. I can call it CO divided by n. Then I can define n as the number of patches, or simply count patches. This is simply the same. And then I can add maybe this. Let's suppose that CO is blue, so that we can okay, be a lighter blue. Okay, and I can add another pen, say red. Okay, and this is O2. status equal to 2. Okay. So suppose that in recolor, instead of black, instead of white, we have blue. And okay. So maybe we can all this we can call reset surface. So to reset surface and okay. So if I now have a button, say, that makes a scan of several values of ACO, I can easily reset the surface without resetting everything. And because the CA also clears the plot, so I cannot keep the old values. And here I think we have to put the y max to 1, since these two quantities range from 0 to 1. Then we may change the go. Say, let's call this as a step, or this, and suppose that go is repeat count patches step. So just to speed up the simulation, one step of go is to repeat several times for the number of it is a one Monte Carlo step, essentially. So number of patches, how many patches are, the possibility of updating, and then we can tick, or maybe no, not here, because tick also refreshes the plot. So I want to tick when I change something, the value of ACO. So we make another button scan. So to scan, we can set ACO to 0. Then while ACO is less than 1, I can reset the surface. I repeat, I call go for several amount of times. So repeat, say 100 go, and tick, which should update the plot also. And then I increase ACO plus, I don't know, 0.01. Okay, so we have seen that this while is essentially the way of doing loops using a classical iterative procedure, like I don't know, a do in Fortran, a for in several other languages. Don't forget, when you use while, to put also the increment condition, otherwise it does not, it halts here. And I may save this as a catalyst scan, okay, and see what happens. So here, instead of this step, I use the scan button. So if I put the scan, I see, okay, just halt. I had to set up in order to reset also the plot. Scan. So you can see that it starts up to now. There is a coverage of O. Then we have the crossover between O2 and CO. We may say show legend, so we can have a reading. And you see that we have essentially a very small window in which this model actually works as a true catalyst. So if one want to continue on this, one could also add, say, the possibility of moving of the two species, and this could be an improvement. So let's try to put, say, another slide there, say, called movement, which is the possibility, again, a probability of, say, switching pairs of sites, so the status of pairs of sites. So to movement, we can to move, say, movement is the probability. To move, to diffuse, say, okay, let's call diffusion instead of movement. Diffusion. So to diffuse, ask one of patches, let say I want to switch the status of these patches with the status of a neighboring one. So I can save other status. No, say let X one of neighbors 4. This neighbors 4. So X is one of the neighbors. Clearly, if they have the same state, nothing happens. But so okay, we can waste a bit of computation time. So let new status of X. Ask X set the status of myself. So this myself refers always to the one who is asking something to do something. So in this case, it is the one patches that I'm calling here that ask X to do something. So myself refers to the status of the calling patch. Clearly, I could have simply defined my status, and instead of this, I could have said set the status, my status. So according to which one you prefer, you can either use myself or simply define a temporary variable storing the state of the calling patch and asking the other patch to set the status to my status, recolor, and then I change my status. So set status, new status, recolor. And okay, so this is the diffusion step. Then in the Go, I can step and then diffuse, say with a certain probability. If random float 1 less than diffusion, diffuse. For instance, so I alternate one step of reaction. This could be a reaction. In this case, to reaction. And one step of diffusion, or react, say. React, so you can use maybe diffuse. No, diffuse is a keyword. To diffuse a step, and this can be, so to be consistent, a react step, because diffusion is a procedure to diffuse some quantity among the steps. I can show you here. Okay, let me take a window, NetLogo dictionary, diffuse. You can ask a patch to diffuse a certain variable among neighbors or among the 4 nearest neighbors with a certain probability. I never use this, but it can be interesting to implement a diffusion procedure. Okay, so let's see what happens if I have a diffusion equal to 0. Nothing should change. So we should observe the same behavior as before. So at a certain point, we have this small window. Now let's see what happens if I have a certain. Oops, I have to halt to reset. So scan with a high version of diffusion. I should check if it is working. But okay, let's see what happens here. Nothing. So something is not really. Okay, let's see. Okay, it is slower. Okay, so if this is what I remembered, if we increase the diffusion of substances, we have, say, a larger window, and yes, I remember well. So you can still have the poisoning by CO, but you are avoiding essentially the poisoning by O2. This is exactly what I remembered from, say, this simulation done several years ago. So you can see that this is a nice phenomenon that is evident only in a spatial version of the simulation. Clearly, if you do the computation using the classical approach by differential equation, you don't see this influence of diffusion, because essentially you are assuming always complete diffusion. So I can save it as catalyst scan, catalyst diffusion scan. Okay, so that you can play also with this. Okay, do you have some suggestion? Otherwise, I can show you. If you want, I can also save this, duplicate, and I can move to say in the same directory. So if you want, you can have a look. Not really a very important. I don't remember which one is. No, this one probably. My drive, teaching, NetLogo. Okay, so if you want, this is the model with some more sophisticated reaction results, but the essence is the same. Okay, so if you don't have suggestions, I would show you a completely different subject. So how to use NetLogo not for performing experiments with the agents, but as a display tool. So I would like to show you this implementation here. This is an interface that I developed in order to show the behavior of the logistic map. I don't know if you know this theme. The idea is this one. When you study a problem of, say, bacteria that grows if they have something to eat, you normally write down a differential equation in which you say that the increment of the number of bacteria depends on how many bacteria are there. And then so we can try to okay, then we can try to implement all this. So let me simply sketch the equations. If I'm able to write down with my this. So yes, suppose that X is the number of bacteria. I don't know why it is not working here. For fraction of bacteria. Maybe better if I write down no, I'm not I cannot use this okay. Well, in any case, then you write something like this: x dot. Okay, let me you install the iPad, otherwise it is essentially impossible to do this. I should have done this before. Okay, so I can extend this. Okay, let me see if it works. Okay. Now I can move this here, and then I can share the other screen. This one. Okay, maybe now you can see the equations. Okay, X is the X is the number of bacteria divided the maximum number of bacteria. So suppose that it is the coverage. Essentially, you have your surface with the maximum number of bacteria, and this is proportional to X. Then the equation is something like this. So each bacteria in the unit of time produces a number of, say, other bacteria, and so in this case you have the exponential growth. But clearly, when you start from a single point, you increase the size, even though you are mixing everything, at a certain point you reach the total. So when X is equal to 1, you should stop. So in order to model this, you add typically this behavior, and clearly this is called the logistic equation. And okay, it gives you a fixed point that depends on A. So if you start with all essentially like this, all initial number of bacteria, they can decrease or increase, and they always reach this, unless you start from 0. Clearly, this is if A is greater than 0. Clearly, if A is less than 0, you go to 0. Unless you start from 0, in this case, clearly, you always stay in 0, even though this is not stable. But if I remember, in 1973, Robert May, who is, I think it is still alive, a mathematician who was studying insects, said, okay, actually insects do not behave like bacteria. They generally lay eggs, then they die, and the next time eggs hatch, so they produce new bugs that can lay. If they have a lot of food, they can lay again eggs. If they have not enough food, they die. And so essentially the time is discrete. So the idea now is that X is again the number of bugs divided by the maximum number of bugs. And A is again the reproduction rate of, so how much egg one bug can lay, divided by something. But now you say that X at the time t plus 1, so next year, is A X times 1 minus X. So writing in a more compact way, it is like this now, the equation. So essentially, this is now a discrete equation, not a differential equation, which has quite a different behavior with respect to the logistic one. The logistic one, which is this one, say, let me call B instead of A because it is not the same. B x1 minus x. This can be approximated by approximating the derivative, which is like this. This can be written is in this way: plus bx times 1 minus x delta t. So essentially, you see that it is slightly different from this. First of all, because the A here is essentially given by the identity plus B delta T. So the logistic map behaves like the logistic equation only when A is very near to 1, greater than 1. Okay, so let's see what how we can use a NetLogo to illustrate the behavior of the logistic map. And this could be another different way of using NetLogo. So let me switch again to sharing the NetLogo window. Okay, so in this case, I want to, first of all, plot the behavior of the map by changing the A. So the map itself is just a parabola, because this is I'm plotting AX times minus 1 minus X, which is this parabola. For the moment, I do not consider this. I can put this here. So first of all, I use a NetLogo to show the behavior of this equation, so this expression, AX times 1 minus X, for A from 0, in which case everything is 0, to 4, which is the maximum value, otherwise it exits the unit interval. Then I should compute X prime equal to this. So if I start from X0, this is the value of X prime. But I want to iterate this several times. So I have to report the value of X prime on the axis X in order to iterate for the next year. And this is mostly easily done using the bisectrix. So this is the value, this is the first value, X0. Then this is the value at time 1. This is again the value of time 1 as reported in the X at time 0. So that this is now the value at time 2. And then by increasing this, I can show several iterations of this map. This is the time series of the values, and this is the histogram of the values. So in this way, we can start to say, okay, if A is less than 1, it means that every bug lays less, in average, less than 1 egg per generation. Clearly, everything is going to be extinct. It is the same as having B less than 0 in the logistic equation. And so you see that actually, for every value of X0, the value goes to 0. This is the time series that goes exponentially to 0, and the histogram is essentially centered around 0. If I use more time steps, I see essentially a delta peak in 0. And by increasing A, I can have now, if A is greater than 1, this is essentially the behavior of the logistic equation. We have another state. Clearly, if I start from 0, I always stay in 0. But if I start from a value different from 0, it can grow or decrease, arriving to a fixed point at a certain value. And indeed, you see that the value in 0 becomes a fixed point at a certain value of the population size. Okay, now if I increase the reproduction rate, you see the the fixed point increases, which is reasonable, but after a certain value, you see that first of all, you still have a fixed point, but it is reached oscillating. We can see better if I decrease the number of steps. And so you see that the oscillation becomes more and more pronounced until at a certain point, instead of a fixed point, I have a limit cycle. So a stable oscillation of a population. And this is essentially what is observed in several insects. So that the population stably oscillates in size from year to year. And then if you increase again the reproduction rate, you can have a period doubling. So instead of just a cycle of period 2, you have a cycle of period 4. You see now 4 values of the histogram. And then you can have period doubling with 8 and so on until you have chaos and the histogram becomes broad. Then you can have a periodic windows inside the chaos. And finally, so this is, for instance, a periodic window of period 3. You see that you can have a transient, but then you go into the periodic behavior with the histogram equal to 3. And so finally, you can have a fully developed chaos with all values covered. You see that you have unpredictable behavior and so on. Okay, this is all done using plots because these are essentially all plots. Okay. So it is a plot with several values, so you can use a plot. And the world is essentially hidden below one of these plots. I don't remember, it is outside the, let me see if I start deleting everything. First of all, the word should appear. I don't remember where it is. Here it is. Okay, it was simply below, hidden below one of the plots. So in this case, I don't even use the plot. Yes. Okay. Okay, I have several things hidden below. I don't remember what is this one. And I use just plots. So one way of using NetLogo, for instance, is to use just the plot capability and integrate equation of motion and something like this. Another possibility that I shall show you in a moment. This is again the logistic map. Now I want to show you in a concise way what happens when you change the value of A. So in this case, I want to, here in the horizontal axis are the values of A, even though let me change it. This should be an old version. To set up, say start A0, start X0. Okay. Set up. Okay. So now I want to show in just one plot, let me show, and x1, which is more clear. What is happening in the logistic map? So in the horizontal axis there is the a value A. In the vertical axis there is the value of this map after a long transient, which is 5,000 steps. So essentially I start with a random value of for each given value of A. I start with a random value of X. I iterate 5,000 times this map, and then I plot 1,000 points. Each of these are 1,000 points on the same location, which is essentially the asymptotic state. So you see that here is the value A equal to 1. So up to here, only the asymptotic state x equal to 0 is present. Here you have a bifurcation. So there is still the solution x equal to 0, which is now unstable, and the stable point appears. That is stable until essentially x equal to 3, which is this. And then this is 3. Then we have the period, the appearance of a limit cycle. Then we have a period doubling, 4 cycles, and then period doubling again, then chaos, periodic windows, and so on. This is the Lyapunov exponent, is another thing. So this is, but for what concerns NetLogo, here I use a plot. These are monitors, but this is the world. And so here I'm using the fact that a turtle can mark a point on this plot. And one thing that could be nice is that I now use again the features of NetLogo that I shall explain to select, essentially to change the values of minus x, max x, minus a, max a. This should be maybe stay here. In order to have the effect of, say, increasing or zooming, I may maybe increase the plot length. And this is nice because in this model we have a kind of self-similar behavior, so that when you zoom in a region, you see again the same features. So again, period doubling, even though I'm zooming in a very, very small region. And this is the standard bifurcation diagram. So this is a slightly tricky how to do this. It is not so short code. I copied in from another model, but the idea is that here I have a turtle that essentially you see here x is a random number. Then I compute a, which is essentially this is the loop for all the pixels. This is a very large world, 600 pixels. So for each of the pixels, this is I compute the value of A, which is proportional to the I divided by the width of the word times the interval end of start A plus the start. Then for a certain transient, I just iterate the map. And then for this, which is the plot length defined here, I compute the coordinates, the y coordinates. If it is inside the word, I ask a patch corresponding to this value to become black. And so essentially this is the dot that appear here. While for the selection of the region, for the selection of the region, I'm using essentially, so who wrote down this procedure is using essentially a turtle that so you see there is a turtle that draws this rectangle here. So when I click here, when I click, it remembers the original point, and then each time I move the mouse, keeping the button down, there is a turtle that draws this square, this rectangle here. Pen up, move to start patch, pen down, and then it moves to the patches that correspond to the mouse down. So we can do this. So the other interesting fact is that I can use NetLogo as a simple display system. Okay, clearly this can be done in JavaScript or Python using some interface and so on, but it can be mixed together in order to, say, define a region and do something on this region according to the buttons. Is it clear what I illustrated? Clearly, I can save these models also in the folder, so that you can check. Probably it is already here. Okay. This and also the logistic map, save as, shared drives, no, not shared drives, my drive, teaching, NetLogo 2025, save. Okay. So, so this is another example of using NetLogo. And okay, so if you have again some particular interest, you may ask. Otherwise, let me check. No, this is a wrong. Let me check what is already inside your oh, okay, so so maybe we can I can show you another example of this rectangle selection. For instance, in another fractal, which is Mandelbrot. I don't know if you know the Mandelbrot system. Okay, this is also a nice. I don't remember why it is. I don't know why it is so skewed, but okay. Leave it now. So the Mandelbrot system is essentially it is an example of fractal, but it is essentially given by a map, in this case in the complex plane. So the idea is that maybe I can show the Wikipedia page of Mandelbrot. So the idea is the following. You use a very simple map that the value of a given complex number times t plus 1 is z square, z, plus a constant. And this sample is, so this can go to essentially infinite or remain confined in some region. And so essentially what you show here is the sample of the C values, this constant, such that this map, this black region, do not go to infinity, while the color of the outside region is colored differently according to the speed with which it goes to infinity. Essentially, the idea is that you iterate for, say, 50 times, and then if the absolute value of this number is, say, above 1000, you color it in black, otherwise in red, otherwise in blue, and so on. So here I show, so the black one is the set of numbers C such that the map is not going in infinity. So here you have the number of iterations, here the threshold for deciding if it stays here or not. The color codes are the value of this. But the important point is that with this I can illustrate the map here. So this is the complex plane. This one of these points, I think this one in the middle, is the beginning of my iteration. And these are all the iterations. So you see that if I do something in the black region, it may make a cycle, and these are the values of z, but essentially they stay always, so can be a triangle like this, a spiral, or something, or a star, or something like this, but it always is confined. Otherwise, if I click on the colored, you see that it goes essentially to infinite. So clearly I have to go to stay near, otherwise you don't see essentially nothing here. but here it goes to several large values. And again, I can use the trick of selecting a rectangle in order to enlarge the definition. So now you see that if I go very, very near, not so near, okay, you have still oscillation. At certain point, it goes to infinity. And now we can enjoy the fractal nature of the Mandelbrot set. So you see that there are small islands of stability inside the world of instability. And these islands have a very, very fractal shape, so that here still, well, maybe the resolution, so I have to check because it seems to go to infinity. Well, should stay confined, but doesn't not really seem to be confined. So let's check. Clearly, I have to check if numerically everything is working. So let's explore this region here. So a point here should stay confined, like a point here. And let me see here. If I go here, I'm still confined. And so you see that, let's try again on some region, I don't know, here. So a point here should stay, again confined, but it should also happen here. Let me check. Okay, so something is working. So you see that we have a really nice fractal structure. With say finer and finer details. Clearly, NetLogo at a certain point is not working very well, but you still see that actually this black and here, because clearly we have a finite resolution. So I click somewhere, but I'm not sure that the true value. This is a rectangle. Okay. The true value is the one, because I'm selecting a patch. So this is the resolution is done at the level of patches. And every patch has a certain value of the constant, and they start to iterate. So again, most of the code is to track a mouse to select the rectangle. This is copied from the other problem. Here I only ask patches to iterate their value of the map, this one. So according to the value of C, which is now called X0, Y0, they have a certain evolution. Probably I'm wrong in the sense that when I click select point, no, but okay, I consider the case because I take the coordinates of the mouse, but I ask the patch to give its value of X0, Y0, because clearly these do not really correspond always, almost never to the coordinates of the patches, because the coordinates of the patches are integers and these are floating points. So we have to to ask the patch to give the value used to color here in order to be sure, but something is not really working. It seems that that everything is correct with respect to these points here. Okay, I think that I'll show you different usage of NetLogo also for showing some mathematical aspect or integrating equation motions or things that are slightly different from making simulation of agent-based models. Clearly, NetLogo was designed to do this kind of simulation, but can also be used as a standard, as a specialized drawing device. Okay, I think that for today it is enough, since I have shown you the interface. Clearly, the code is quite long. I have not written from scratch, otherwise it could have taken, say, several hours. But I think that if you go to the shared folder and examine the examples that I provided, you can take profit of what I've shown to you. Are there questions or comments? Otherwise, I would stop here for today, and for the last lesson, I would again ask you to, first of all, try to work with NetLogo, and so try to develop the very simple starting examples in order to signal if you find something that you don't understand. So take profit of my presence in the last lesson, and also suggest possible models that I can try to implement. Otherwise, I shall show you things from my past experience. Okay, if it is okay, I can stop my presentation and see you. Goodbye to next Tuesday.
Thank you, Professor.
Thank you. Goodbye.
Goodbye.
Okay. Bye.
Thank you. Bye.
Bye. Thank you.
Thank you. Bye.
Bye.
Bye-bye.